So if we have four constraints over each of our intervals, we've got our two measured values, the y's at each endpoint and the two gradients at each endpoint. What this means is that a cubic polynomial ends up being a popular choice for obtaining a smooth piecewise interpolation function. And we've illustrated a typical cubic polynomial here. It's a polynomial in x, and it has an x cubed term down to a constant term. So we end up having four coefficients, c0 up to c3. And so because of the fact that we have four coefficients and we have four constraints, that is why we end up having a cubic polynomial as a popular choice for this type of smooth interpolation. And so for the rest of the lecture, for the smooth interpolation part, we're just going to talk about cubic polynomials. So a little bit of terminology then. Piecewise cubic interpolation is just the fact that we're fitting a cubic polynomial to each interval in our successive knot points. And what we're going to be talking about specifically is piecewise cubic Hermite interpolation, and that is where we make the fit in a particular way, and we do it by specifying the values of our first derivatives and the values of our measurements at the endpoints of each interval. So that this is the specific method that we use when we specify the y values and the gradient values at the endpoints of the interval. That method of defining the constraints is known as Hermite interpolation. So we have this polynomial, which is here shown by p of x in terms of its coefficients c3 down to c0. And what we'd like to do is we'd like to find the correct coefficients, the c3, c2, c1, c0, such that the polynomial evaluated at the start of the interval is equal to yk, and the polynomial evaluated at the end of the interval is equal to yk plus 1. But also we have these derivatives constraints as well. So if you take the derivative of the polynomial at the beginning, you should get gk, and if you take the derivative of the polynomial at the end of the interval, you should get gk plus 1. And so we can write this out explicitly in full as a set of four simultaneous equations in the values of c3 down to c0. And I've written these all out here in 4 lines. So the top line here corresponds to the constraint that we meet this measured value at the start of the interval, and the second row is the derivative of p being equal to the gradient at the start of the interval. The third row is the constraint that we meet the measured value at the end of the interval, which corresponds to this equation here, and then the final row shows that the derivative of p needs to be equal to the gradient at the end point of the interval. So we've written it just as 4 simultaneous equations. And we can rearrange this into a matrix form. So here we have exactly the same data, or the same set of equations really, as we had on the previous slide. I'll just toggle back briefly. So here in matrix form is the same information. These are the values that are being multiplied by the c's in order to meet the constraints on yk and gk, and the yk plus 1 and gk plus 1 values and the gradients at the start and the end of the interval. So what we know, the values that we know, are all the xk's and xk plus 1s. We know where our knot point locations are, and we also know our measured values and our gradient values at the start and the end point of the interval. And what we don't know, what we'd like to find out, are our values for the coefficients, the c's in this case. And so we have a equation in the form ax plus b, ax equals to b, and this can be solved with standard tools such as MATLAB. So you can write this matrix out perhaps and invert it and then multiply it by b to get a solution. This not really x, I should have written c here to make it match up correctly. And then we would obtain expressions for each of the coefficients of C. And we'd be able to write out these coefficients in terms of our xk's and yk's and gk's and so on. So as we've seen, it's possible to set up a system of equations so that we can solve and find the coefficients of the polynomial that we can use for our piecewise cubic fit. But there is actually a neater form that we can use to do this cubic Hermite interpolation. And in order to do it, we need to recall the local variable u that we defined earlier. And that is sort of shown here again. So it's a fraction of the distance from x to the start of the interval as a proportion of the whole width of the interval, from xk to xk plus 1. And so when we're at the start of the interval, u is equal to 0, and when we're at the end of the interval, u is equal to 1. And we used it before for the linear interpolation function. So if you want to interpolate for a given value of u, then you blend together the y value at the start and the y value at the end of the interval by a value of u. And this works for any interval up from 1 up to n. So in our context, we're going to use 4 cubics that are written in terms of u. So these are 4 cubics that are defined on the interval from 0 up to 1. And so there's the first one here, h1, with the black continuous line. There's the second one here, h2, with the red continuous line. And there's the h3 here with the black continuous line, and h4 with the red, a black dashed line here, and h4 with the red dashed line. And this is just a factorization of them for anybody who's interested in that kind of thing. And these 4 functions here, these 4 cubic polynomials that are defined for u from 0 to 1, they're known as the cubic Hermite basis functions. And they're chosen very specially. They're chosen so that their values, measured values, their height, and their derivatives are very carefully chosen. So for example, h1 has values that goes from 1 down to 0. h2 starts at 0 but finishes at 1. h3 and h4, both of them start at 0 and end at 0. If we look at their gradients this time, then h1 is horizontal at the beginning, h1 is horizontal at the beginning and at the end of the interval, so it has 0 derivative. And the same is true for h2. This red solid curve here is horizontal at the beginning and the end of the interval. Whereas h3 has a gradient of 1 at the beginning, but no gradient at the end. And h4 has no gradient at the beginning and a gradient of 1 at the end. So this is what makes these 4 functions special, the fact that their gradients and their values at the beginning and the end of the interval are specially chosen. So as we've seen, for each interval on our data, we have some values, y's, and some gradients, here shown as the g's, that we'd like our smooth function to fit. It's illustrated here. The height of each red point is the measured value, and the gradients are shown by these green direction lines here. We'd like our smooth cubic polynomial to pass through the points with these directions. So we can actually use our Hermite basis functions that we defined on the previous slides to write out an interpolating function for our data. And it's written out as a blend of our values, our y's, and our gradients, our g's. And these values and gradients are weighted by our basis functions. It's as simple as that. So we can take our 4 basis functions and we can weight them. And the basis functions are also weighted by the interval widths as well, so depending on the interval widths, which if our interval width is fixed, say at equal to 1, then that becomes very simple indeed. So what it does is it provides us with a cubic polynomial, a long cubic polynomial for each interval written in terms of the local coordinate u. And this is the same polynomial if we write it out in full. So if we take h1 and write it out in full, it looks like that, and h2, write it out in full, it looks like that, and the same for h3 and h4. And here is our y's, our measured values, and our gradients, our g's. So that's all very good, but what we still need is some way of defining or deciding on what the gradients should be at the beginning and the end of the interval. And there are lots of different ways that we can use to specify our gradients for each of our knot points, going from k up to k equals 1 up to k equals n. And each way that we use to specify a gradient actually gives us a different interpolation scheme. So when people talk about different cubic interpolation schemes, what they're really talking about are different ways of defining what the gradients should be as you go through. And once you've defined your gradients, you can write out your cubic polynomial for any of your intervals, and therefore you can interpolate a value between any two successive knot points. So we need a way of specifying our gradients, and this next couple of slides illustrates one way in which we can do this definition of our gradients. And this specific way of defining gradients is known as the method of Catmull-Rom interpolation, and that's just the names of the people who came up with the way of doing it. It's a very simple scheme. So you have some measured values shown here by the red points. And if you want to define a gradient at a particular knot point location, here xk, what you do is you look at the information at the knot points on either side. So you look at xk minus 1, and you look at yk minus 1, and you see what their measured y values are. So what's the height of each point on either side of our knot point. And so the gradient at xk, the gradient of the line going through xk, is going to be the same as the gradient of the line that joins the previous and following knot points. So that's just here the difference between yk plus 1 and yk minus 1 divided by the difference between xk plus 1 and xk minus 1. So this length here divided by this length here, or the other way around rather. So so the gradient at a particular knot point is defined by the gradient of the line that joins the previous and the following knot points. Now clearly that will only work for values of k where we do have a previous and a following knot point. So we need to think about the endpoints, which we'll do in a minute. So this is just to illustrate how the gradients are calculated over all of the knot points. Ignore the endpoints for now. So we can see that each of the interior knot points, the ones that are not at the ends, has a line that is defined based on the previous and following knot points. But at the endpoints we can do something fairly simple as well. So the gradient at the first knot point should be the same as the line joining the first and second knot points, and the gradient at the last knot point should be the same as the gradient of the line joining the last knot point to the previous one, which we can see here by these lines here. So we've defined our gradients using our y values, using the lines that join the knot points either on either side or the first or the second, and so on. And so that means that we have values for our g's, we have values for gk for all of our values, and we have our measured values y as well. So that means that we can now in a position to build our piecewise interpolating function for every interval. So for the interval from xk to xk plus 1, we can define it like this. So here's another example of cubic Hermite interpolation. This one is known as De-Boor interpolation, again named after its inventor. And it's exactly the same as Catmull-Rom interpolation, except it calculates the gradients in a different way. So just recall that we already insist that the values and the gradients at our knot points should match on the left and the right. So that means that at a given knot point, we have two functions, one on either side, one for the interval to the right and one for the interval to the left. The constraint that we have this measured y value and the constraint that we have this direction is actually fixed for this knot point, and it means that the function on the right has to match these constraints at the beginning, and the function on the left has to match these constraints on the right. That's just written out more formally here. So if we take the left hand function and evaluate it at its endpoint at u equals 1, then we need to be equal to yk. And if we take our right hand function fk and we evaluate it at its starting point, which is u equals 0, then that also should be equal to yk. So these functions should match on their value at their left and right endpoints respectively. Similarly, the gradient of the left-hand function evaluated when u equals 1 should be equal to gk, and the gradient of our right-hand function evaluated at the start should also be equal to gk. This is just what the Hermite interpolation conditions require us to satisfy. The thing that De-Boor interpolation brings to this is they have a second constraint, a new kind of constraint, is that we need to make sure that the second derivatives this time also match at each knot point. So the left-hand function should have a second derivative that is equal to the right-hand function evaluated at the start of its interval. So left-hand function at the end, second derivative should match right-hand function at the end, its second derivative. So this is the constraint for De-Boor interpolation. And if we go into the maths of this, we can use this to calculate the gradients gk. So we specify this constraint, and that determines for us a set of gradients that end up matching these constraints. And we can use it to set up a system of equations to find our gradients at each of our knot points. And this system of equations can be written in matrix form, as we've seen before. So there'll be a matrix A, a vector containing all of our gradients here, shown as G, and a vector V that is defined based on the actual data that we've seen, the measured y values that we've observed for our data. And that's shown on the next slide here. So here's our matrix A, our gradient vector, gradient full of G's, and our vector V here. So the matrix A is fixed, it's always the same, right? So you can store it once and constantly in memory, right? And so it's here, just all the rows are 1, 4, and 1, except for at the beginning and the end. Everything that's not written out here is actually 0. So this empty space here, they're just zeros. So this might be a very large matrix if you've got lots and lots of knot points, but actually it's very sparse. There's only numbers on the main diagonal and the line above the main diagonal and the line below the main diagonal. And here's our matrix G. This is actually the matrix of gradient. I say matrix. It's a vector G, a vector of gradients, and this is what we're trying to find. And here's our vector V. Our vector V is determined by our data. So the measured y values that we've observed, the measured y values that we've collected at each of our knot points, they are placed, differences between them are placed into the elements here. And the W value here is the width of our intervals between each pair of successive knot points. And the assumption here is that for De-Boor interpolation, the width of each interval has to be the same across all successive intervals. So we can solve for G, we can find G by inverting this fixed matrix A, and again computationally that's easy because the matrix A never changes, so we can calculate its inverse once and once only, and then when we observe our data we can calculate our V vector, pre-multiply it by the inverse of A, and that will give us our gradients G. And as we've seen before, once we've obtained our gradients for all of our data, we already have our y values that we've observed, then we can use the Hermite basis functions to define a interpolating function for each of our intervals, so we can get our piecewise interpolating functions over our whole data range, and we have a smooth cubic interpolating function. So this slide is just to illustrate a comparison between the two different methods that we've seen for cubic Hermite interpolation. So these two different methods that both differ in the way that they calculate their gradients. So we had Catmull-Rom interpolation that defined its gradients by the gradients of lines that join things like previous and following knot points. And we had De-Boor interpolation, where the gradients were defined by a constraint that was expressed on the second derivatives of the function. So we've shown here on the top row, for the same data, for the same observed y values, the red points here, two interpolations, once with Catmull-Rom and once with De-Boor interpolation. And on the second row, we've calculated the gradient of the two interpolating functions. So this here is the gradient of the Catmull-Rom interpolator, and this is the gradient of the De-Boor interpolator. And then we can carry on with that, and we can look at the second derivatives of each of these. So this is the second derivative of this function, or in other words, this is the gradient of the first derivative, and likewise this is the second derivative of the De-Boor interpolator. So the main thing to notice, I guess, here is that the second derivative function for the Catmull-Rom interpolator has some discontinuities in it. It breaks up, whereas the De-Boor interpolator is continuous in its second derivative. There's no breaks in its second derivative, and that is by definition of the De-Boor interpolator. That's one of the constraints that it has. So even though the De-Boor interpolator probably looks like it varies a little bit more wildly than the Catmull-Rom interpolator, its derivatives are actually better behaved than the Catmull-Rom interpolator. So as a summary in these slides, what we've looked at are the main sort of take-home points, I guess, are the fact that we have discrete data, but we sometimes need to have continuous representations for that data. And we might want to get continuous functional estimates from our discrete data through methods that are either interpolation within the data range, approximation where we allow some error, and extrapolation where we go beyond the data range. And we looked at full polynomial interpolation where we fit a single function to all of our data, and we've looked at piecewise interpolation where we fit separate functions for each interval based on our knot points, based on our data locations. So we looked at linear piecewise interpolation, which is continuous but not quite differentiable, not smooth, has some sort of jagged corners. We looked at nearest neighbour interpolation, which is almost continuous but not quite, has those breaks halfway between the knot points. And we've looked at smooth interpolation, mainly in the form of cubic Hermite interpolation. It's continuous, it's smooth, but it does need the gradients to be specified as well as the original measurements that we obtained. And we looked at two examples of that. We looked at Catmull-Rom and De-Boor interpolation that are both cubic Hermite but differ on how their gradients are calculated.